we're recording. So let's talk a little bit about homework 4. I think I'm really fuzzy too. Let's see, homework 4. All right, thanks for the attendance notes. So I want to go over the homework, and then I want to finish talking about crypto by looking at the RSA algorithm, and then if there's a few minutes left after all of that, we'll go ahead and we'll start talking about mathematical induction, which will be our next big unit. And in some ways will be like a highlight of the course. But let's start with the homework. So so question 1 was about fallacies, and we have 2 fallacies we deal with. The first one is this, where if P then Q, and Q is true, and so we try to conclude that P is true. And this is a fallacy. And the fallacy is affirming the conclusion. So here's an example. Let P be the proposition, it rains. Let Q be the proposition, the grass is wet. Alright, so if it rains, then the grass is wet. That's a conditional statement that we believe is true. Suppose Q is also true. Suppose the grass is wet. Can we conclude that it rained? Not necessarily. It could be that someone, used a garden hose and sprayed down the grass. So that's an example where this is true and this is true, but this does not have to be true. It might be that it did not rain and somebody, watered the grass. So that would be an example of specific propositions where you can demonstrate that in that case P does not follow from those first 2 propositions. And then denying the hypothesis looks like this. So if P then Q, not P, therefore not Q. So we can use the same pair of propositions. If it rains, then the grass is wet. That's true. Not P says it did not rain. Can we conclude that the grass is not wet? And again, we can't, because, the grass might be wet for some other reason. Maybe the sprinkler turned on. So that's a demonstration of an example where this is not true. The thing about fallacies, if you're trying to show this does not follow from those, you really only need to show one example where that happens. And a single counterexample is enough to state that a theorem is false, right? And it doesn't mean that this can never be true. What we're saying is that this does not logically follow from these 2 statements. But it could be that if it rains, the grass is wet. It didn't rain and the grass is not wet. That could happen. But we're not saying that Q has got to be true or it's got to be false. We're saying Q does not follow from these 2 things. So it's a statement about the truth of the proposition. P implies Q, comma, not P, gives us not Q, and we're saying this is false. All right, and then the even-odd questions. If n is even, 6n plus 4 is even. So prove.
On that last one.
Yeah.
The fallacies. Since we're not showing it mathematically, we just have to show a counterexample, and that's considered enough. I guess I'm having an argument. It seems like, oh, we're doing all these mathematical proofs. We're gonna go this step, this is proves this, and and these were just like,
So the way I wrote that question said define propositions and use them to give a real-world example of 2 fallacies we discussed. So we're not trying to do a rigorous proof. We're just looking for an example of 2 propositions that show these fallacies. Does that make sense?
guess that, like I said, the hard part for me is you know, I think it's because we've been doing this very rigorously that when we come to this thing, we say, well, you know, the grass isn't wet, therefore it couldn't rain, is silly because the grass can be wet for other reasons.
Right.
That's enough. That's enough of an argument saying.
So questions 2 through 6 all start with the word prove, right? And if a question starts with the word prove, you want to do a rigorous proof like we've been doing with, you know, statements with numbers and justifications and so on and so forth. Question 1 simply says define P and Q and use them to give examples of two fallacies. So that's a looser requirement, right? We're not trying to do something that's a formal proof in this case. We're just basically finding words to you know, give an example of this fallacy and that fallacy. And the goal there is really just, you know, to get some experience with what's a common situation where, you know, this conclusion wouldn't follow from those hypotheses. If it's sunny, then I run. Doesn't immediately mean since I run it is sunny. Well, that's an interesting thing to think about. So conditional statements are not causal, right? So let S be the proposition it's sunny, and let R be the proposition I run. And suppose that this is a true statement. Suppose anytime it's sunny, I go out and I run. Right? If that is absolutely a true statement, then this is also true. If I don't run, then it's not sunny. But it's not implying a cause and effect. It's not like as soon as I take off my jacket, clouds will appear and the sun will go away. Right? It's a statement of the fact that if this is true, then that must be true. If I'm not running, it cannot be sunny, not because I control the weather, but because I've already asserted if it's sunny, I'm running. Right? So we live in a temporal state of existence where things come one after another, and we believe that there's a cause-effect associated with that. So necessarily when we read an if-then statement, we think of the then as happening, you know, sometime in time after the if. But that's not what's going on with these, right? And that's tricky to sort of keep straight.
So with that one, if it's sunny, I run. Well, what if it's, well, it doesn't, we're not saying it, but, well, if it's rainy, I also run.
Mm-hmm. Yeah, so it's very possible that, you know, if it's sunny, I run, and it's not sunny, it's possible that I also run, right? If we claim that, you know, if it's not sunny, I'm not going to run, that's that fallacy of denying the hypothesis, right? And this is not logical. So if it's not sunny, this says nothing about whether or not I run. Right, that's the whole key to this fallacy. If it is sunny, we know I run. If it's not sunny, no idea. Maybe I run, maybe I don't.
But the it's I didn't run, therefore it's not sunny is true?
This is true, yeah. If I don't run, it's not sunny.
Right, because I've said I always run when it's sunny.
Yeah, exactly.
Okay, so even if I run when it's wet, the fact that I didn't run means it's not sunny.
Yep, you got it.
That's tricky.
Yeah, it is. Definitely. Logic is a tricky subject because, you know, it relates to something very basic, which is how we think, you know. And sometimes when we, you know, especially when we're doing proofs or we're asking, you know, does this follow from that? Our intuitive understanding of these concepts can actually get in the way, right? In some sense, calculus, if you're asked to take an integral of something and you have to do a trig substitution, we don't really have a lot of daily experience around that, so we just follow the steps, you know, and the answer pops out hopefully at the end. And this, because it relates to, you know, not just an everyday thing, but something so fundamental, it can actually be a lot harder to work with. All right, so let's look at number 2, and maybe 3 and 4 and 5. I think we've already talked about, but let's do a full version of number 2. Prove that if n is even, then 6n plus 4 is even. And remember, the definition of even is that your number can be written as twice an integer. Okay, that's what we start with. So we're trying to prove if this thing, then that thing. We're allowed to assume the hypothesis. So we can start off and say n is even. That's a hypothesis. We're not allowed to assume this. As soon as we assume this, everything else depends on 6n plus 4 being even. And in particular, there's no way we can prove 6n plus 4 is even if we start off by assuming 6n plus 4 is even, right? So we can assume this because what we're trying to do is say if this is true, let's show that that is true. So we can state the hypothesis, but you can't use the conclusion as part of your proof. Because if eventually you come to the conclusion, all you've said is this is true if this is true. And that doesn't prove this is true. So about your only option here is use the definition of even. So there exists some integer, let's call it k, such that n equals 2 times k. That's the definition of even. And then you play around with this, you stir at it, you go back and you try other things, and so on and so forth. Yeah, I said don't start the proof with the conclusion. So you can do that, yeah. That's kind of what we're going to do here. You could prove that if 2 divides n, then 2 divides b times n. And if 2 divides b times n and 2 divides c, then 2 divides b times n plus c. And then you could just substitute in 6 and 4 for b and c. That's a more general proof, but that's totally legit. So yeah, start with the hypothesis. Don't start with the conclusion. And then let's just substitute this n into 6n plus 4. And this is not the conclusion. I'm not saying 6n plus 4 is even. Okay? I'm saying 6n plus 4 equals 6 times 2k plus 4, because I've set n equal to 2k, where k is an integer. And this is equal to 12k plus 4. But I can factor a 2 out of that and say this is equal to 2 times 6k plus 2. And this is substitution from 2 and algebra. Backwards e is there exists, correct? So there exists an integer k such that n equals 2 times k. Alright, well I've shown 6n plus 4 equals 2 times 6k plus 2. And now I'm just going to say, therefore, 6n plus 4 is even. And the reason for that is 6k plus 2 is an int. And that's, you know, properties of ints and definition of even. I could make a separate step where I state 6k plus 2 is an integer, and I could call it j and so on, but this is the spirit of it, right? So I started with n is even. That's the hypothesis, so I can assume that, and then that means n is equal to twice some integer. And then I just said 6n plus 4 is equal to this, that, and that. And in doing that, right, I showed 6n plus 4 was twice an integer, therefore 6n plus 4 is even. And it's really critical to note that nowhere did I assume the hypothesis, the conclusion, right? So don't use the conclusion as part of your proof. If I were to make an assumption, 6n plus 4 is even, 6n plus 4 equals 2 times an integer, and so on and so forth, everything after that depends on this being true. And I don't know if that's true. That's the whole ball game. I'm trying to prove this. If I haven't already proven it, everything else in the proof is contingent on this being true. Let's see, what if you claim there exists an integer j such that 4 equals 2j as a definition of even? Oh, you mean to get like from here to here, maybe?
Yeah, I was just trying to prove that 4 also is even. So is even.
Okay, yeah, you could do that. You could also, just state 4 equals 2 times 2, therefore 4 is even. That would work. You don't have to say there exists a j, you could simply say 4 equals 2 times 2, and therefore is even. If we wanted to go in the other direction, if we wanted to prove that if 6n plus 4 is even, then n is even, that's a whole different ball game. And in fact, that will turn out to be not a true proposition, because if n is 1, 6n plus 4 is 10, that's even. So this can be even though n's not even. So if you argue this in the other direction and you end up with a QED, there's probably a problem somewhere. But here we're saying this implies that. All right, and let's go ahead and do number 3. Prove if n is even, then n squared plus n is even. And this is not much different from just proving that n squared will be even. It's the same kind of thing. Start off, n is even. That's the hypothesis. There exists a k such that n equals 2k. That's definition of even. And then plug in. So n squared plus n equals 2k squared plus 2k equals 4k squared plus 2k equals 2 times 2k squared plus k. And that's substitution and algebra. And we've written n squared plus n as 2 times n integer, and so n squared plus n is even, because 2k squared plus k is an integer, and this is the definition of even, and that's what we're trying to show. And yeah, if you proved this for b times n plus c, then yeah, this is a particular case of that. So that's super handy. All right, and then 4 and 5. These are one of these was the example we did when we talked about indirect proofs. So prove if n squared is even, then n is even. And this is hard to do directly, because if you write n squared equals 2 times an integer, it's not clear where to go from there. If I say something like, you know, n squared equals 2 times k, it's not clear how to make a statement about n. I mean, other than n equals the square root of 2k, but how do we show that this is twice an integer? Did I forget my QED? Oh, I got one there. So a direct proof is kind of elusive here, but an indirect proof works really well. So we can do a proof by contradiction. So assume n is odd. So that's negation of the conclusion. And n squared is even. That's the hypothesis. And we're going to find a contradiction, right? So we're saying n squared is even. That's the conditional we've been told. And we're going to assume this statement is false. We're going to assume n squared is even, but for some value of n turns out to be odd. And so now we can say, you know, n equals 2k plus 1 for some integer k. And that's the definition of odd. And then we can substitute n squared equals 2k plus 1 squared equals 4k squared plus 4k plus 1 equals 2 times 2k squared plus 2k plus 1. That's substitution of 3 and algebra. And this tells us, you know, n squared is odd, because it's twice an integer plus 1. So 2k squared plus k is an integer, and the definition of odd. And that's a contradiction, because we previously stated as true n squared is even, and here we've got n squared is odd. Since we reached a contradiction, this assumption must be wrong, and so therefore n is not odd, and so n is even. And the same thing happens for question 5. Prove if n squared is odd, then n is odd. We'll make the assumption that n is even, n will be 2k, n squared will be 4k squared, which is 2 times 2k squared. N squared will have to be even as well. And so that contradicts n squared is odd.
For these problems, we had a choice, though. We could have done direct or indirect.
Mm-hmm.
Right?
Yep. Yeah. Let's see, we didn't say that 2k squared plus 2k is odd. All we need to know is that this is an integer. But this whole thing now is 2 times an integer plus 1, which is odd. But it doesn't matter what this integer value is and whether that's an even or an odd integer. But the whole thing, which is n squared, is twice an integer plus 1. That's odd. Reasoning next to n squared is odd. This one. N squared is twice an integer plus 1. That's the definition of odd. So 2k squared plus 2k is contained in z. That just means it's an integer. And so this is 2 times some integer plus 1. Yeah, the odd was down here. Can you prove that something's not even and odd at the same time? I mean, we know that something's either even or odd, but how could we prove that a number can't be both even and odd?
You would use both of the definitions of odd and even at the same time, and you use algebraic manipulation to work it into a fallacy because the definitions are different.
Yeah, exactly. Prove n is not both even and odd. So, you know, step one, n is even and odd. That's, you know, the negation of the statement. And we just need to find a contradiction. Well, if n is even, there exists, you know, some k such that n equals 2k. That's the definition of even. Since n is odd, there exists a j such that n equals 2j plus 1. That's a definition of odd. And so we can combine those, and since 2k is equal to n and n is equal to 2j plus 1, 2k is equal to 2j plus 1, 2k minus 2j is equal to 1, 2 times k minus j is equal to 1, 1 is odd, and that's a contradiction. Or divide both sides by 2, and you can show there's two integers whose difference is 1/2, and that's a contradiction of properties of integers. So the machinery we know at this point is really powerful. I mean, we can make statements and prove them about some pretty fundamental, important characteristics about numbers and evens and odds and so on and so forth.
Can you show that last page again?
Yeah. So I guess technically pi would not be even and it would not be odd because it's not twice an integer and it's not twice an integer plus 1. So if we allowed even and odd to be applied to any number, there'd be some numbers that were neither even nor odd. Now if you made a mathematical system where some numbers could be both, that might be interesting. See what you come up with. Got a bunny that keeps coming in the backyard, so we put out some parsley to see if we can get it to come over. That's what I'm looking out the window for. All right, so let's look at number 6. So let's prove if a divides x and a divides y, then a divides 5x minus 3y. And this is again just using the definitions. So statement 1, a divides x, that's a hypothesis. So there exists a k such that x equals a times k. That's the definition of divides. And then a divides y. That's a hypothesis. And so there exists a j, which is an integer such that y equals a times j. That's again the definition of divides. And now I'm going to do something that I'm totally allowed to do, even if there's no motivation for it. I'm just going to do some substitution and say 5x minus 3y equals 5 times. And for x, I'll do ak, and for y, I'll do a times j, and that's substitution of 2 and 4. and this is equal to, and I'll just multiply it out, 5ak minus 3aj, and then I'll factor out an a, which is a times 5k minus 3j, and that's algebra. And then I'll say, you know, because 5x minus 3y is equal to this, a divides 5x minus 3y. And that's because 5k minus 3j is an integer, and the definition of divides. And that's what we're trying to show. Line 2 says x equals a times k. Because our hypothesis is a divides x, which means x is a multiple of a. The definition of divisibility means that x is equal to a times some integer. Right? That's what this pipe symbol means. And then the same thing on line 4, because a divides y. Y is a possibly different multiple of a, so a times j. All right. Any questions on the current homework assignment?
Do we have another week to do it?
Nah, you don't want to do that. Yeah, then we'd miss out on the really fun homeworks later. Can't figure out how to get started on 2 and 4 through 6. Let me pull up the homework and see what those look like. Let's see what we got. Homework 5. Let's see. Get started on 2. So 2 you can do just by like trial and error, right? To tell if a number is prime, just try dividing it by anything other than itself in 1. If you can look at a number and immediately see a factor, like if you look at the number, you know, a number that ends in a 5 or a 0, you know it's divisible by 5. If you see an even number, you know it's divisible by 2. So some of these you might look at and immediately see, hey, you know, this is a number that can be written as a product of others. But if you see a number and you can't think of a factor of it, just try to find a factor up to the square root. And you don't have to go beyond the square root. So square root of 103 is, you know, a little above 10. So you really only need to know if it's divisible by 2, 3, 5, or 7. So it's just 4 trial divisions. And then questions 4 through 6. So should we go over Euclid's algorithm again? Give me a thumb.
Why not do a review?
Yeah. Let's do that. So and these are in the other videos, so you can go through the topic list and find them like that. But and people know about the topic list for this course, right? Hopefully. There's a link to it in Canvas, but if you do linuxengrcs.com/shared/videos, there's a running timestamp log, and you can search through this. So Euclid's algorithm was on October 18th, and it's 40 minutes and 32 seconds into the video. And if you go to that video for October 18th, there'll be a clickable link for Euclid's algorithm. And if you go to the video list, which is not updated every day, but I try to update it pretty frequently, right? You can click through to that and find Euclid's algorithm, and it'll take you into where we started talking about that. But let's run through Euclid's algorithm here, and then this also talks about Fermat's little theorem. And modular exponentiation, I think, was handled in the previous on the 15th, yeah, so the previous class. But let's do Euclid's algorithm, because that one is probably the quirkiest, and we'll refer to it later today anyway. Yeah, that link should be on Canvas. So Euclid's algorithm is a way to find the greatest common factor of two numbers. So let me dream up a reasonably interesting example here. Hold on a second. And let's see. I'm horrible at coming up with good Euclid's algorithm problems. This is just one of those things. Yeah, there should be a link on Canvas. So link to the lecture videos takes you here, and link to the timestamp index takes you there. Oh, but the video link's not up there. Yeah, I don't update the video link every time, but yeah, just go back up one level and find the video list, or just, you know, go through the whole playlist. All right, let's just do a random GCD problem. So let's find the greatest common divisor of 72 and 50. All right, so we take our first number and we write it as something times the second number plus some remainder. So 72 will be 1 times 50 plus 22. And then we're going to use this number, what was, you know, the second number, and the remainder. And we're going to say 50 equals something times 22 plus something. Well, 22 goes in twice, that gets you to 44, you've got 6 left over. And we're going to use what was the second number, 22, and this remainder for the third step. So we're going to write 22 as something times 6 plus something left over. So 6 goes into 22 3 times, it leaves you 4 left over at the end. And we're just going to keep doing this. 6 equals something times 4 plus something. 4 goes in once with 2 left over. Carry these over again. 4 equals something times 2 plus something. Well, 2 goes in twice and there's 0 left over. Once you get to that, then this last number that we would have carried down to the next step, that's the greatest common divisor, or greatest common factor. All right, any questions on that? All right, so I'd say go back, watch the videos. If it's still not clicking for you, come by office on Monday, and we can talk about it then. Basically modulo over and over again. That's kind of what this whole unit is, right? Yeah, it's just reducing repeatedly. And there's a lot of cool stuff you can do with this. One thing we can do with this is if we know the greatest common divisor is 2, we can find numbers a and b such that 72a plus 50b is equal to 2. And we're guaranteed to be able to do that. And we can do that actually from the way we got down to this 2, we can work backwards. And in particular, if two things are relatively prime, if their greatest common divisor is 1, we can find a linear combination of those two numbers that's equal to 1. And that's going to be useful in RSA.
Turns out it's also in math age.
Yeah. 223, I usually do an assignment where people have to write their own GCD algorithm in Java, and so you get to revisit this again there. All right, so let's wrap up RSA. So we talked on Wednesday about the idea of a public key crypto system. Public key meaning you can freely advertise how people should encrypt a message. And it does not disclose the key that you need to decrypt. And that's asymmetric because you know, most ciphers, if you know how to encrypt, you automatically know how to decrypt. Shift cipher, if you encrypt by adding n, you decrypt by subtracting n, or adding minus n. And so an asymmetric cipher, you can tell people how to encrypt. That does not tell them how to decrypt. That would be a good ODP. That'd be a fun one to do. All right, so let me just show you the algorithm here, and we'll go through a slightly hand-wavy justification that this works. But you know, this is not something you're going to need to do for a test or anything like that. If you take a crypto course later, you'll probably actually code this, and that's fun to have done. But here's the basic setup for RSA. So let P and Q be hopefully large primes. Now when you do this, you know, by hand for a test, you'd use, you know, 5 and 7 or something. But think, you know, hundreds of digits worth of prime numbers for these. All right. So we set n equal to p times q. So n is an even bigger number. And n is only divisible by two things other than itself in one. It's divisible by p and it's divisible by q. And if p and q are close to each other, then you know, if n has 400 digits, p and q have about 200 digits each. Now, you know, if p is the number 3 and q is something close to n, it's not very hard to factor. You divide n by 3, hey, it's divisible by 3. But if these are big, right, to get to p and q through trial division would not be practical time-wise. So n is equal to p times q. And find some number e that's relatively prime to p minus 1 times q minus 1. And there's ways to do that. So you find a number that's not divisible, doesn't have any factors in common with p minus 1 and q minus 1. And this is your public encryption key. This is the key that you advertise to the world along with this product n. So your key equals this pair n comma e.
What does relatively prime mean again?
Oh, GCD equals 1. So the GCD of e and, in this case, p minus 1 times q minus 1 is equal to 1. So no common factors. All right, So you want people to be able to send you secure messages. So you say, hey, here's my encryption key, n comma e. It's a pair of numbers. Really big number, really big number. All right. So how do you use this to encrypt a message? Well, first thing we're going to do the simplified character set that we talked about Wednesday. We're just going to use the letters A through Z. And we're going to number those 00, 01, 02 all the way up to 25. So it's a 2-digit number for each letter of your message. And the largest value that a letter has is 25. That's the letter Z, right? So we're going to break your message into blocks of a certain length. And each letter, you know, corresponds to a 2-digit number. And so depending on how many letters we have, for example, if we have 4 letters, we could have, you know, a number up to 25252525, right? If we broke your message into blocks of 5 letters, we could get a 10-digit number up to, you know, 2525252525, right? So pick the largest number of letters such that this is always less than n. Alright, so this is just chunkifying your message. So for example, if n equals, you know, if that was your number n, right? We could have 1, 2, 3, 4. Looks like we could have 4 characters, right? Because the largest 4-character message would be, you know, this. And this number is smaller than n. But if we had a 5th character, potentially, you know, our message could look like this. And that's a 10-digit number, and this is only a 9-digit number, so this would be too big for n. So we're just fixing a block size to be as big as possible, but not so big that your message ends up being bigger than n. And the reason for that is we're going to do lots of stuff modulo n. And if your numbers are smaller than n, then, you know, things are unique. If we have a number that's bigger than n, it could be congruent to something smaller than n, and now things aren't unique anymore. So we're just fixing our block size based on the size of n, little n. All right, and so so since we know what the primes p and q are that gave us n, right, we can do the following. So if you know p and q, you can find an integer d such that d times e is congruent to 1 modulo p minus 1 times q minus 1. All right, how do we do that? Well, we can do that because we picked e to be relatively prime, which means the greatest common divisor of this and that is 1, which, as I mentioned really quickly a little while ago, that means we can find a linear combination of this and that, which is equal to 1, which we can use to find a number d such that d times e is equal to 1 mod that big number. All right, so we can find this d because we know what the p and q were originally. But if you just hand somebody n and e, there's no known way to practically figure out what d is. Right, it's a computationally complex thing. So e is public and d is something we keep private. That's part of our secret decryption method. All right, so how do we encrypt our message? Let m be the message. This is in plain text. All right. Alright, so it's a bunch of two-digit numbers strung together. You just treat it like an integer. Right? So if your message is ABC, then M would be, 10203. It's actually a 01, but, it's a 0. So 10,203, that would be the message corresponding to ABC. So M's the message, right? The plain text version of this. To encrypt, we take M and we raise it to the power E and we reduce modulo N. And remember, we're telling the world, hey, here's my encryption key, N and E. So what do? Take your message, raise it to that power, reduce it modulo that number. Alright, and E, might have, 100 digits, and N might have 100 digits. So these are large operations to perform, but that's why we have, modular exponentiation, things like that. I would not be surprised if that happened someday or somewhere, or maybe in some slightly parallel universe. If people started trying to control prime numbers, that would be interesting. That would be a cool story, actually.
That'd be a great snack.
I know, right? The Prime Syndicate or something like that.
Hope you didn't patent that.
Nope, it's public domain. Go for it. All right. So this is how we encrypt, right? Take your message, raise it to the power E, reduce it modulo N, and you get some big long number. Okay, and that's the encrypted version of your message. Okay, so how do we decrypt? And this is where all the magic comes in. So so the first thing is, we found a number D originally, such that D times E is congruent to 1 mod P minus 1 Q minus 1. Okay, so D times E, and we're the only people who know D. So D times 1 is 1 more than a multiple of P minus 1 Q minus 1. Alright, so to be 1 more than a multiple of that means that DE is equal to 1 plus some integer times P minus 1 times Q minus 1, where K is an integer. And so if we take C and we raise it to the D, so C is the ciphertext, right? If we just raise that to the power of D, well, since C is M to the E, that's M to the E raised to the D, and exponents say this is the same as M raised to the D times E, which is M raised to the, well, D times E is 1 plus K times P minus 1 times Q minus 1, which is M times M to the K times P minus 1 times Q minus 1. So if we take the ciphertext and we raise it to the power of D, it's equal to this gargantuan number. M, our original message, times M raised to this power. Alright, so I'll mark that with a star. And we'll come back to it. Alright, so let's just look at part of that expression. Let's look at M raised to the K times P minus 1 times Q minus 1. We'll say considered. Yeah. All right. So we're going to make an assumption here that's almost guaranteed to be safe. You're welcome. Let's assume M and P. Let's just assume the greatest common divisor of M comma P is equal to 1, and the greatest common divisor of M comma Q is equal to 1. In other words, M can't be a multiple of P. Okay. Oh yeah. Go ahead and do an attendance ping. Let me know if you're still awake. So P is a really big prime, Q is a really big prime, M is a message that we got by taking, you know, our characters and changing them into numbers from 0 to 25. Almost impossible that that's going to turn out to be a multiple of P. If it is, do something, throw an extra, you know, character at the end or something like that. And you're good to go. So, and if this was, you know, general ASCII characters, we could throw, you know, a null terminator at the end, an extra one or something. So this is a safe assumption, right? So M and P have no common divisors. So here we pull out Fermat's little theorem. And Fermat's little theorem says M to the P minus 1 is congruent to 1 modulo P. And also M to the Q minus 1 is congruent to 1 modulo Q. All right, so this expression, M to the K times P minus 1 times Q minus 1, this is also M to the P minus 1 raised to the K times Q minus 1. And if we work modulo P, M to the P minus 1 is congruent to 1. So this is congruent to the 1 raised to the K times Q minus 1, which is just 1 modulo P. And similarly, M to the K times P minus 1 times Q minus 1 we can show is congruent to 1 modulo Q. Fermat's little theorem. So our original C raised to the power D is congruent to M times, well, if M to the K times P minus 1 times Q minus 1 is congruent to 1, it's just congruent to M times 1, which is just M modulo Q, and it's also congruent to M modulo P. Yeah, I know, and like one is such a little theorem, the other one is so huge, which I think is why they call it the little theorem. So C to the D will be congruent to M both mod P and mod Q, and here we can pull out the Chinese remainder theorem. And a Chinese remainder theorem will tell us that C to the D is congruent to M modulo P times Q. And remember, P times Q is just N. So what all of this, yeah, you'll have to do this from memory on the midterm. No, this is not on the midterm. So what all of this means is you start off with a plain text message. You tell the world, my encryption key is N comma E. Somebody can take M, raise it to the E modulo N. That gives you ciphertext. Right? They can send that to you on the open airwaves. Other people can read it, but it's just some big number. But if you have this decryption key, all you do is take that message, raise it to the power D, and that'll turn out to be congruent to the original message mod N. And since the original message is less than P times Q, raise C to the D, reduce it modulo N, there's your original message.
Can I see that equation one more time for the decryption?
This one.
Thank you.
Mm-hmm. So that's super hand wavy, right? Yeah, if you can crack RSA, then you can have an A on the midterm. I actually saw a cute comic for a computer security class. It was the last class, and the teacher said, you know, your grades have been recorded. Everybody got an F. They're on the school's computer. Have a good summer. The grades will be recorded on Monday. And so basically, you know, students had to like figure out how to hack into the system to change their grade before Monday. All right. So that's just an example of why this stuff is relevant to us as computer scientists, right? It's a big part of computers today is security and hashes and encryption and things like that. And it all comes out of this number theory. I mean, Fermat's little theorem is hundreds of years old, and we're using it for this stuff, which is kind of cool.
I thought so. This is how RSA works, right?
Mm-hmm.
So I was under the impression before that essentially there would be an encrypt key and a decrypt key on each machine, and then a public encrypt and decrypt key on each machine, so they can send an encrypted message across the wire, and then they still have to have the private decryption key on each machine. But
Yeah, so for one-way communication, right, there's a public encrypt and a private decrypt. And if you want to do two-way, you need a pair of keys. But in each case, the encrypt is public, the decrypt is private.
seems like another way you can do this.
Yeah. And I believe you could, encrypt with D and decrypt with E. Same thing is still going to get you there. And if you publicize D, right, then you have to find the E that makes D times E equal to 1, or congruent to 1, and so on. But yeah, the usual setup is crypting the message, public domain. So like on your emails at the bottom, your signature can include your encryption key. And then if somebody wants to respond to you, they use that to take their email message to you, encrypt it, and send that. And you're the only person with the corresponding decryption key, and so you can read their message. Nobody else can. There should be a Capture the Flag Club at Clark. Wouldn't that be cool? Maybe when we're back in person. That would be fun.
I would love to join one, but I wouldn't even know how to start.
Well, that would be a good reason to have one, right? Because most of us don't have any experience with that. But I mean, with any kind of sort of target in mind, right? That's a great way to learn stuff. And I think it would be really cool if people wanted to try to get into that and figure out some of the basics, and then have some competitions or something. There's so many pathways to learning. But the common key is, you got to have a desire to get there. And if you can find a goal that you want to get to, and a path that starts with where you are right now, right, then all you need is time and energy, right, which is a lot. But I think that would be really cool. Capture the flag. So I've never done one, but I've seen them portrayed in movies. But it's hacking contests, so a blue team and a red team basically, and trying to exploit weaknesses or vulnerabilities in the system, and trying to protect against those and things like that. And when I was in school, we wanted to figure out how the operating system worked, and the operating system was proprietary, so there was no information, there were no books we could find on it, and so on. But just like going into the system and changing things and seeing what happens, and sometimes crashing it, and stuff like that. But if you have goals, it's really a good way to sort of find a path to understanding.
On that last line, the change theorem, there's an N above the P and Q. Is that also like, what is that?
This is what P times Q is equal to.
Oh,
So
it's
N
times.
is P times Q, yeah. Oh, probably. You could make a compiler that automatically like decrypts before it compiles, and you keep your source codes encrypted. That would be fun. Or at least like ROT13 them or something.
You
Yeah.
want to be able to get your source code at
Totally.
some point, right?
Yeah.
It's also not very open source friendly, you know?
This is
You gotta-
true.
You gotta fight the power.
Yeah. Obfuscating object code would be interesting. It's kind of hard to read anyway, right? Well, for me at least. Cool. All right. Any other comments, questions about this? Like I say, this is not on the exam. This is not something you need to be able to do. I want you to understand what a public key versus a symmetric cipher
Timer for 3 minutes.
is, but other than that, is that Captain Jack? But other than that, right, I'm not going to ask you about details of this algorithm, or ask you to work it out or anything like that. And I won't ask you to code it, but it's good to code at least once. All right. So let's move on. We've got another 15 minutes. So let's talk about mathematical induction. And this is our next part of the course. And it's in some ways, you know, certainly one of the most important, if not the most important, thing to get out of this class is the idea of induction. Induction is something that we sort of do all the time when we're thinking about algorithms and we're thinking about whether or not something works, and particularly when we're writing code. You know, how do we know that our code's going to play high-low? Well, we can work through a specific example and say, hey, this code works. And maybe we can think abstractly and think, you know, whatever number somebody guesses, this will work, right? But how do we, like, actually know that? How would we prove that to ourselves? And a lot of times when you're trying to convince yourself that an algorithm is correct, you find the following situation. You can think about it with some simple cases. If I, you know, have an algorithm that's supposed to invert a matrix, well, so if my matrix is you know, 1 by 1, this will work, and if it's 2 by 2, it'll work, and if it's 3 by 3, let me scratch out some pieces of paper. Yeah, that looks like that works. How do I know it works for 4 by 4? And what you find is that the way that you went from, say, proving this for, you know, a small case to a slightly larger case is completely general. And it feels inside like, you know, I could do a proof for the next more complex case, but I don't have to because I know that I could do it, right? And so I'm convinced that this is going to work. And when you have a situation where you can see how to get, you know, to whatever step you want, in other words, if you want to prove an algorithm works for n equals 1,000,000, you don't necessarily need to prove it for n equals 1,000,000 if you know that it works for, you know, small values of n, and you can see that if it works for this value of n, it'll work for a slightly bigger value. And if you can convince yourself of that, then you can say, okay, if I just repeated this, you know, 1,000,000 times, I could prove this works for 1,000,000. Okay, that's where mathematical induction comes in. And it's basically a way for us to kind of make rigorous this intuition that we often get about generalizing things. And so let me give you a bit of a motivating example. And we won't prove this using induction, but I want to give you some specifics around what I just said. Let's see, what do I want to do? Do I want to do De Morgan or something else? Let's do... Let's just do commutativity of set operations. I knew I'd spelled something wrong in there. For example, when we talked about set theory, I told you without stating why that this is true. If we take A1 union A2, we get the same set as if we do A2 union A1. And that's the only thing I said as far as unions being commutative. So this is given. And now I ask you a question, prove the following. Prove that if I take this union of 3 sets in the opposite order, I still get the same thing. And without knowing anything about A1, A2, A3, we can do this really just using this fact. And we could do this as follows. I could say A1 union A2 is equal to A2 union A1. That's given. I'm not going to write this like a formal proof. This is just a motivating example. And so A1 union A2 union A3 is the same as A2 union A1 union A3. Which is, you know, I can do these 2 unions first. And this rule says if I take the union of 2 things, I can switch the order. Well, here's one thing, here's another thing. This says I can switch the order. So this would be A3 union A2 union A1. And if we assume associativity, parentheses don't matter, this is A3 union A2 union A1. And so by knowing this, I can prove this. This is equal to this. Now suppose I wanted to prove this. I could do exactly the same thing, right? I could use this previous result to say that, hey, this is the same thing as this. And so this thing unioned A4 would be the same thing as A4 unioned with that thing. And it's, you know, a couple of lines of exactly what I did here, and I can prove this. But now, suppose someone says, for any n bigger than or equal to 2, prove the following. Prove that if I take the union of n sets, that's the same thing as taking the union in the opposite order. And that's a fundamental leap. Right? If I know this for 2, I can prove it for 3. If I know it for 3, I can prove it for 4. If I wanted to prove it for 5, I could take this and I could prove it for 5. And then I could prove it for 6 and so on. And so if you said prove this for n equals 100, I could do it. It would take 100 pages of paper, but it's doable. But how do you make the leap to say, hey, it's true for any n bigger than or equal to 2? It's true for 3, 4, 100, 1,000, 1,000,000, a zillion. How do we do that without actually going through a zillion pieces of paper and working our way up and showing this? And the answer is going to be mathematical induction. And mathematical induction will let us take what we did, for example, to go from 2 to 3 or from 3 to 4, and it'll let us generalize it in a way that's completely rigorous, as opposed to just keep doing this until you get up to n sets. Okay, that's why we're going to spend some time studying and learning and using mathematical induction, because it lets us make this intuitive leap rigorous. All right, so what's the basic idea here? Think about a ladder. So we've got rung 1, 2, 3, and so on, and up here is rung n. And you want to know, is it possible by climbing this ladder to eventually get up to rung n? And n might be 10, could be a relatively short ladder. N could be, 100, a really tall ladder on a fire truck. N could be, a billion. It's a ladder going up to the moon, maybe, right? And we want to know, is it possible to reach step n? And to answer yes, we only need to know two things. The first thing is, if you're at step n, at step k, you can get to step k plus 1. That's the first requirement. You got to be able to go up one more step. And so, we bring in someone who understands human physiology and muscle and so on and so forth, and we say, hey, if you're standing right here, is it possible to go up one more rung on this ladder? And presumably they would say yes, as long as you've eaten and you don't have, thin air and so on. Yeah, if you're on rung K, you can always get to rung K plus 1. The other thing you need to know is you can get to step 1. You got to be able to reach this step. If this ladder is sitting on top of the Empire State Building, I may not be able to get to the first step. But if I can get to the first step, and if it's true that whatever step I'm on, I can go up one step more, you can prove that you can reach any rung number n for any positive integer n. And how do you do it? Well, you start on step 1. We're assuming you can get to step 1. And whatever it is that you do to go from step k to k plus 1, you do that here, which will take you from step 1 to step 1 plus 1 is 2. And once you're on step 2, you do this again, which will take you from step 2 to step 2 plus 1 is 3. And from step 3, you do it again to get to step 4, and again to get to step 5. And if you keep doing that, eventually you'll get to step n. And it's a little like that whole, journey of 1,000 miles begins with a single step, right? If you can take one more step, you can eventually, cover any distance that you want. Now, if the air is going to get so thin that you're going to pass out when you get past rung 1 million, then this first statement is not true. It may be that when you're at rung, 999,999, you can't get to step 1 million because you're going to pass out from the thin air, right? But if this is true and this is true, you're guaranteed you can get to any step n. And that's what mathematical induction is. And to apply this to problems in this course, we're going to basically change your question into a statement about propositions, about a family of propositions. And we're going to try to establish these two facts, that you can get to, some case like step 1, and that if you're at some case k, you can get to a case k plus 1. And if we have those two things, then we'll be able to say, therefore, by mathematical induction, you can get to step n, where n's any integer bigger than or equal to 1. So that's our plan for next week. We'll probably spend the whole week talking about this. We'll go through this in some detail. We'll add specifics to this, and then we'll start working through some examples and doing some proofs using this. And we'll do some proofs that are very mathematical. We'll do some proofs that are very kind of touchy-feely, wiggly, but that all use the same principle of mathematical induction. We'll talk a little bit about why this works, why being able to do these two things lets you do, lets you make the statement that you can do this for n. And we'll look at some ways to misuse this. We'll see some pitfalls we can run into and so on and so forth. And so we'll do this almost certainly all of next week and the week after. This will not be on the midterm, okay? Everything up through this is fair game for the midterm, right? And I already said I'm not going to test you on details of RSA, but basically everything up through and including number theory is fair game for the midterm. Mathematical induction will not be on the midterm. That'll be on the final. So we'll dig into this on Monday. I'll make a few comments about the midterm. Midterm will be on Wednesday, and then Friday we'll continue with induction. All right, send me one more attendance note on the way out, and have a good weekend. I will see you on Monday. All right, have a good one.
I'll ask you a question real quick.